Picture an obsessive scrapbooker who, every single day, takes a fresh, full photo of her entire desk and slips it into an album. She does not jot down little notes like moved one pen. She just snaps the whole desk again. The clever part is her glue. If a coffee mug looks exactly like yesterday's mug, she reuses that same printed photo of the mug instead of printing it twice. So each new page is a complete picture of the desk, yet the album barely grows, because anything unchanged is just pointed back at the old print. That habit of saving full snapshots while quietly sharing the unchanged parts is exactly what your version history does. We call each snapshot a commit. Most developers use commits every day without knowing that a commit is a complete snapshot, not a set of edits. That gap leads to confusion about how Git stores a year of history in a few megabytes and how it can restore any version instantly. Git is a content addressable database. Every piece of data is stored as an object whose name is the SHA, one hash of its own content. There are 3 core object types. A blob holds the raw bytes of one file. A tree holds a directory listing, mapping names to blob or subtree hashes. A commit holds one top tree, a parent link, and metadata. Because names come from content, identical content is stored only once, and any corruption changes the hash, so it is detectable. When you stage files with git add, Git compresses each file's content with slib, computes its 40-character SHA, one hash, and writes it to .git/objects under a path built from that hash. For example, objects/e6/9-29, using the first 2 hex characters as a folder. The staging index records each stage file's path alongside its blob hash, so the index already knows the exact content of your next snapshot. At git commit, Git turns the index into tree objects, 1 per directory, each listing file names with their mode, type, and the hash of the blob or subtree they contain. Git writes a commit object containing the hash of the top tree, the hash of the parent commit, the author and committer names with timestamps, and your message. Git computes the SHA, one of that commit object, and that hash becomes the commit ID you see in git log. Git updates the current branch ref, the file under .git/refs/heads, to hold this new commit hash, so the branch label slides forward to your snapshot. The ref log at .git/logs records the old and new hash, giving you a safety net to recover the previous position. Later, Git GC bundles loose objects into a compressed pack file and stores files that differ only slightly as deltas against each other to shrink disk usage. Imagine a 500-file project where you change one line in one file. Git writes exactly 1 new blob for the changed file, 1 or more new tree objects for the directories along its path, and 1 new commit object. The other 499 files reuse their existing blobs by hash, so the commit is a full snapshot of all 500 files, but costs only the storage of what changed. The biggest misconception is that a commit stores a diff of added and removed lines. It does not. A commit references a complete tree of the project at that moment. Git computes diffs on demand by comparing 2 trees when you run git diff or git show. Another myth is that pack file deltas mean commits are diffs, but deltas are a storage optimization applied later, fully separate from the snapshot model. Just like the scrapbooker reusing yesterday's mug photo, a commit is a hashed object pointing to a full tree snapshot and a parent. Branches are just refs holding the latest commit hash, and unchanged files are shared by hash, so history stays tiny. I take one tool you use daily and show you the real machinery underneath it every single day. So subscribe to TechWithJoel. Want me to do a live Git cat file walk through a real repo next? Comment yes if you do. Subscribe to TechWithJoel.